it's great to tell you about not just the dreams that we have, but all the really hard work that my group has been up to. For the last couple years, I've been at Oregon this is my 5th year, and my group has been up to a lot of really interesting things. And a major focus of my group is studying porous materials and what happens to them when they become nanocrystals, and all the size-dependent behavior that emerges once you do that. So research in my group focuses on not just porous materials, framework materials, anything with a high surface area, sometimes two-dimensional materials. So these include metal organic frameworks, metal chalcogenide materials. We're interested in perovskite materials. And when we study all of these different classes of materials, we're interested in 3 main areas. How do we make them as nanoparticles? We're interested in how do you understand charge transport through something that's mostly empty space? We like to call this ion-coupled charge transport. And then we're interested in how do all of those things change given the uniquely dynamic bonding that exists in these materials. And so I'm calling these 3 separate areas, but really in every project that we study, all of these focuses come into play, and I think you'll see that today. So in our lab, okay. In our lab, we focus very much on a class of materials known as metal organic frameworks. Metal organic frameworks are composed of organic components that have multiple functional groups that can bind metal sites. You combine these with different metals, and you end up with a huge array of materials. One estimate is that there's about 100,000 distinct structure types, and that's not even counting the materials that are isostructural with each other, where the only difference is the metal ion. So there's 100,000 distinct structures. And so because of this vast tunability, people have imagined fundamental questions as well as real-world technological questions that people are interested in that they can tackle with these materials. But I would argue that of all the different areas that people are studying with metal organic frameworks, it's really gas capture, and I think we're gonna have a delay here. Okay. It's gas capture, environmental remediation, chemical separations that are all going to have the greatest impact, at least so far. So Saudi Aramco is really interested in using them for these purposes, ExxonMobil. And the reason for this is because there's an estimate that, should we try to, okay. Thank you. The reason for this is one estimate is that about half of all energy that is consumed every year by industry goes into separating chemicals. So that's every year, half of all energy. And the reason for this is because we still rely on these distillation-based processes. So this is a still, like the statue, except this one is the size of a skyscraper. And there's an estimate recently that if you could replace these distillation-based processes with a membrane-based alternative, that you would save about 90% of that energy. And so this is why big corporations have become really interested in this idea, because that's a tremendous amount of energy to save. So when people do this, currently they use membranes based on cellulose acetate. And cellulose acetate is nice because it's readily abundant, relatively inexpensive. And so you can use something like cellulose acetate to separate, in this example, methane from CO2. And you can evaluate the performance of these membranes. And when you do this, you can plot how selective your membrane is versus how permeable your membrane is. And people have accumulated enough data to see that as you evaluate more and more membranes, you hit this so-called upper bound. So in the last 20 years or so, Robeson and co-workers identified this upper bound, and reasoned that the reason it comes up is because if a membrane is more selective for some separation, it's probably because things aren't moving through that membrane very easily. And so if something is moving through a membrane really easily, it's probably not going to be very selective for anything you're trying to separate. And so there's a lot of interest in being able to improve this upper bound, to push the performance of membranes to better and better selectivity and permeability. And so for this reason, in the last 15 years or so, people have moved away from cellulose acetate-based membranes and have embraced this idea of a mixed matrix membrane. This is something that includes a moth-based material that's either covalently attached to some polymer, that's the example I'm showing here, or they're simply just mechanically mixed with each other, okay? And so with that better chemical tunability of a moth, people have found that, yeah, you can push the performance beyond those original upper bounds that people identified 20 years ago. And when you use these, practically, this is what they look like. So if you use a moth that is made out of just a bulk powder, you're not really getting a homogeneous mixture of your powder and your film. In fact, if you take a cross-sectional SEM image of what that thing looks like, you get this sort of layered cake thing here. It's because your particles just sediment out at the bottom of your polymer membrane. Here's your polymer, there's your powder. You're not really dealing with a mixed matrix membrane. And as a result, these things are incredibly brittle. So yes, you know, in an academic setting, we can show that the performance is in theory good, but this is so brittle that I took this from a paper where the next photo, the tweezers were simply holding too hard and the whole thing just crumbled into dust, basically. And these need to be able to withstand about 8 atmospheres of pressure in a practical industrial setting if you're trying to separate chemicals. So there's no way that using a bulk powder for a mixed matrix membrane that you're going to be able to do that. So because of this, there's very recently become interest in moving away from mixed matrix membranes that are based on just large bulk powders and move more towards scenarios where by using moth nanoparticles, where either there's a covalent attachment between the moth nanoparticle, for example, if you were to use a polyimide, or if you were to use something like PVDF, where you wouldn't expect there to be an attachment, that not only do you get the mixed matrix membranes that are much more mechanically robust, but now you can have greater selectivity over the separation that you're trying to do. Because even just something as simple as is the polymer attached or not is going to have a profound impact on the performance of the membrane. So, so there's a lot of interest in moving towards moth nanoparticles. The problem is people don't really know a whole lot about how to even make a moth nanoparticle. So this is where my group got interested. This is all pioneered by Checkers Marshall, who's the first person to graduate from my lab, and that happened just before I flew out to come to this. So it's been like a real whirlwind of a week for the Brozek group. So Checkers started on this project, and she said, which moths can even be made as nanocrystals? What sizes are reasonable? And ultimately, what is the chemistry that controls the nanoparticles that you get? And so she looked at the literature and found that of the 100,000 or more moth materials, these are all the ones that people had reported to supposedly make as nanoparticles. And you don't need to squint too hard. I'll tell you that a lot of those are actually the same moth. And so there's really about 6 to 10. Anything that's a circle is a average or median size. Anything that's a triangle is the smallest supposedly reported size. Okay, we're talking about half a micron here. We're not talking about 5 nanometers or 10 nanometers. So to us, this didn't really look like a moth nanoparticle. So we figure, okay, then if this is what the state of the art is, how do we improve upon this? Well, let's think about the model of how, the mechanistic model of how a nanocrystal could even form, because maybe from there we can figure out how to control the size. So when people talk about how particles grow in general, they use this, they invoke the Lemaire model. And the Lemaire model goes something like this. As your reaction proceeds, the precursors for your nanoparticles are going to increase in concentration until you hit a critical threshold. And at that point, the particles will spontaneously nucleate, and the concentration will fall below that point, and then you don't get any more nucleation. You just get growth by diffusion. That's what should happen in theory. And then the sizes will just kind of grow accordingly. Well, when we were looking at the literature, we noticed that this didn't really make sense to apply to moths, because the Lemaire model assumes that you have separate growth and nucleation steps. It also assumes you're working at incredibly high concentrations. You need to be able to precipitate nucleated nanoparticles. But what we saw in the literature is that actually the way that people were making moth nanoparticles was by really decreasing the concentration that you would normally use to make a moth. So that was weird. And then there are also a few, very few, but very well done in situ time-resolved studies to suggest that moths aren't growing by separate nucleation and aggregative growth. It's actually sort of like a continuous polymeric-like process. So we need to come up with a new model to understand how moths grow in general. Not just moth nanoparticles, but how do moths grow in general. So we came up with this alternate model where we say, you know, this process must depend on the organic linkers being deprotonated. People tend to use what they call a modulator, which is typically something just like benzoic acid, so something that looks like an organic linker, but you know, it only has one carboxylate group. So you need that to be deprotonated. You need to form metal linker bonds. You need to form metal modulator bonds. And we reason that the competition of these four equilibria would dictate whether you could trap a moth particle at a given size. And so the way we were thinking about this is that you isolate a particular size by flooding the surface with ligand. That ligand is either excess linker or it's excess modulator, and you basically need to consume all of the metal ions as much as possible on a local concentration level so that the thing can no longer grow. And the ability of your reaction to do this is going to depend on these equilibria. So that was the idea. And based on these equilibria, we reasoned that if you could set up a sequence of reactions and you monitor what happens to the particle size, the more ligand you add, we figured that the particle sizes should decrease. And then at some point, they're going to start increasing again. And this is because we reasoned once you add modulator, you're predominantly favoring the formation of these metal linker bonds. But at some point, you've added so much acid that you favor the protonation of the linker. And because of that, you can no longer trap the moth particles. Instead, now, they have all the time they need to grow. In fact, this isn't really a new idea. You know, and if you ever try to grow a nice big crystal, typically just add a little bit of really strong acid. And in fact, in my PhD lab, there is this moth that Mircea Dinka, the first awardee of the Dream Chemistry Award, there was this moth that he pioneered in grad school, and every time we made it in his lab, we couldn't do the last step, which was he had to come up and add a drop of HCl because he knew just exactly how much HCl to add to get really big crystals. So this has already been intuitive for people for a long time. In fact, there's some data in the literature to suggest that this should be true. So someone previously reported that you could track the size of a moth known as MIL-125 or a separate moth known as UIO66, and you sort of get this predicted U-shaped relationship by simply adding more and more of your modulator, in this case, toluic acid. Okay, so there was some reason to believe that this model sort of made sense. Well, in other words, we said that your modulator should have two roles. At low concentrations, it should act like a capping ligand. It should push sizes to be smaller. And then at some point, it should really just act like an acid and allow your crystals to grow. And so we submitted this for publication, and the reviewers came back and said, that doesn't make any sense. Why would a molecule just change what it's doing? Why would it switch from being a ligand to being an acid? And we said, fine, we'll prove it to you. And if anyone, I don't know if here you use ice tables to deal with equilibria, but it's in the US, when I teach Gen Chem, it is the least favorite thing that students have to do. And I said, well, you know what? We're going to deal with the world's worst ice table. Rather than just one acid and one base, I'm going to say, let's take these four equilibria, and let's assume reasonable equilibrium constants, and let's use typical initial concentrations of their metal and your linker and everything, and let's see what you get in the equilibrium. And so it's really hard to depict the result of a multi-dimensional reaction space here. So this was our best attempt to do it. We said, for a fixed amount of acid, your modulator, how much metal ligand bonds do you form? And how much of your linker stays protonated? And so when you use very small amounts of your modulator, you predominantly form these metal ligand bonds, okay? And at some point, you add so much modulator that you no longer favor making those, and instead you favor making these protonated metal linker bonds. So in other words, there seems to be a region where it acts like a capping ligand. There's a region where it acts like an acid. And by the way, this inversion happens at a very special point. It happens right at the pKa of your modulator. So this makes it more of like a very kind of predictive tool that we should be able to use. So this is all in theory. I don't know how long I've gone into this talk, but so far no experiments yet, really. So we have to show that this, this actually works. And so we took a variety of different iconic MOF materials. In this case, I'm showing copper HKUST1, also known as copper BTC. And we said, well, let's look at all the different synthetic parameters that people typically explore and investigate the impact on particle size. And so these are 3 separate sets of experiments where the only difference is how much modulator we use. So in all these experiments, we're increasing the concentration of the reaction. But the difference between these is how much modulator. And we see that, okay, concentration matters. It kind of pushes the sizes down. But what seems to matter much more is simply how much modulator you used. Another way to explore this is let's vary how much modulator we use. But rather than just throw in benzoic acid, let's throw it in as a buffer. So if we use a buffer mixture where a third of it is in the benzoic acid form and the rest is the benzoate, this is the data we get in yellow here. So the sizes are overall smaller. We get that kind of U-shaped relationship that we predicted. And you could do the exact same reaction and just make the buffer more and more acidified. And for an otherwise identical set of reactions, the particle sizes get bigger. And that's totally consistent with this idea that the modulator stops acting as an effective capping ligand and really just kind of acts like an acid. Okay, so this has become a nice predictive tool for us. Other people have started to pick up on this idea. So Jeff Long's lab had this really nice paper showing you could sort of use a off-the-shelf typical biochemical buffer and apply it to a different set of MOFs. And you have a huge control over what the particle sizes as well as their morphology. So that was nice. Well, we want to take a step back and realize we're not just studying this really small little niche field of MOF nanocrystals. This understanding that we came up with is totally consistent with how people have thought about how crystals grow in general and how polymers grow. So when people talk about the growth of ionic crystals and the growth of polymers, they say that you're going to get the biggest molecular weight species, whether it's a polymer or an ionic crystal, when the stoichiometry of the reaction media looks as much as possible like the stoichiometry of the thing that you're trying to make, okay? So in other words, and this is actually, this is a scheme that I came up with, but this actually very much shows up again and again in the literature for these fields where they say the rate of growth of a polymer or an ionic crystal is maximized at a stoichiometry that looks as much as possible like the thing you're trying to make. And if you move away from that stoichiometry, the rate really falls off. Well, what we're saying is a perfect complement to that. The smallest nanocrystals you can get, you get the smallest nanocrystals when the stoichiometry of your reaction media looks as least as possible like the MOF you're trying to make. In other words, use a ton of excess linker and you're going to end up with really small MOF nanoparticles. So that was the idea. And so this is all complementary to how people think about these other ways that things grow. So now that we can make porous materials as nanocrystals, I wanted to start to do some of the things that people have had fun doing for decades with quantum dots or semiconductor nanocrystals in general. I want to see whether their behavior becomes size dependent. I want to know what happens now that I can take advantage of the fact that they become colloidally stable and I can use them as an ink. I want to take advantage of solution state characterization techniques. I want to be able to use them as thin films. And so that's what my group has had a lot of fun doing in the last couple years. So the first sort of foray into this area, we've been focusing on a MOF known as MIL-125. MIL-125 people like to think of as a porous, molecularly tunable analog to TiO2. So here's TiO2. MIL-125 has this octameric titanium oxo cluster, I'm also showing here. But unlike TiO2, which has a relatively fixed optical gap of 3 EVs, depending how defective it is, TiO2 is often very defective. The optical gap of MIL-125 can be pushed from 4 EV to just 2.5 EV simply by modifying what the ligand coordination environment is around the titanium sites. That's one of the really nice things about these materials. It's a solid, but in some ways you can view the metal like a coordination chemist and say, I'm gonna tune what the ligands are around there, and you have a direct impact on the optical properties because the orbitals around the titanium, they dominate the frontier orbitals, the HOMO and the LUMO, okay? The other reason that we like this material is because all of this photocatalysis that's being done with moths now, it was all inspired by this seminal report by Ferret and others about 15 years ago, where they showed you could take Mil-125, which has titanium 4+, irradiate it in the presence of an alcohol, and it'll go black. The thinking was that you excite an electron to the LUMO, and you can trap it there by oxidizing the alcohol. The alcohol gives up an electron, it fills the hole on the HOMO, and you trap an electron on the titanium. So that was the thought, although it had never really been definitively proven. So this is something that we wanted to tackle. We want to know, does all this become size dependent? And can we use solution state characterization techniques to actually prove that you're making titanium 3+? So to do this, we needed to be able to make Mil-125 as nanoparticles. And we were able to do it by using benzoic acid. We get this kind of U-shaped relationship again. The sizes you get depend on the identity of the ligand of your titanium precursor. We think the stronger the metal ligand bonds, the lower the concentration of titanium in solution, and it's easier to trap smaller particles. So now that we can make these as nanoparticles, we showed that we can make mixed matrix membranes with them by simply treating them as an ink and just doctor blade them, make a self-supported film. It retains that photoactivity, so you could just dunk it in an alcohol, hit it with UV light, and that film turns black. So this is sort of our picture. But we can also use these as a solution and use solution state UV vis spectroscopy. So basically up to this point, if you were to characterize a moth, you had to use solid state techniques. But now we can treat them almost like solutions. And so here's a solution state UV vis spectrum of the particles. And these are the D to D transitions, hallmark D to D transitions for titanium 3+. If you open up a standard undergraduate inorganic textbook of octahedral titanium 3+, this is what you see. Titanium 3+, subject to Jahn-Teller distortion. We can quantify all of it. We can quantify that Jahn-Teller splitting. And the other thing that we know is that this definitively proves this mechanism, that light comes in, you excite an electron from the linker to the metal, and you trap the electron on the titanium by quenching that hole on the linker with an alcohol. Okay, well, this is all nice, but we were wondering, does all this become size dependent? What happens when we make these of different sizes? And so rather than solution state spectroscopy, we turned to solid state spectroscopy because I wanted to be able to measure the optical gap in the absence of any guest molecules. I didn't want any solvent or anything somehow modifying what we saw. And so this is a UV vis spectrum of 80 nanometer particles. And I could collect the data while evacuating them and heating them, so just getting rid of everything that's in there. And when we did this, we saw this really peculiar temperature dependence. The optical gap seemed to be redshifting a lot as we heated it. And we thought maybe this was just this batch of particles. So we tried a different size. So we tried much larger particles, and there's a temperature dependence, but it seems to be much less severe. And I was scratching my head and I was thinking, what could be causing this? And I thought back to my postdoc days when we were studying traditional semiconductors, and I remembered that every semiconductor shows behavior like this. Diamond, silicon, germanium, everything will show that the optical gap will redshift as you heat it, okay? And the reason for this you can think of in terms of simple MO theory. At low temperatures, your atomic orbitals, your atoms are sitting close to each other, they're making really nice strong bonds, there's really good orbital overlap, and so your bonding orbital is really stabilized, and your anti-bonding orbital is really destabilized. You heat up the material, you get a lattice expansion, the atoms, the orbitals aren't overlapping as much, and so your bonding orbital isn't as stabilized, your anti-bonding orbital isn't as destabilized, and so your gap it gets smaller, okay? So that's sort of the molecular explanation. What does this look like in a typical semiconductor? I had a hard time finding actual spectra for what this looks like because the effect is so subtle. And so we collected this data ourselves for TiO2, and this little shift here is what you would expect for TiO2. This is what people had analyzed previously. It shifts the same amount that people had reported. So a very minor effect, minor but reproducible effect. Whereas for us, if we plot the optical gap for 3 different sizes of these moths, you see that they shift a lot. In fact, in the case of 80 nanometer particles, you heat them over a similar temperature range as the data I showed for TiO2, and that optical gap is dropping by almost 500 millieV, which is huge. The other thing, and it's size dependent, so you see the effect is strongest for the smallest particles, and it's the least pronounced for the larger particles. We fitted the data to something called the O'Donnell and Chen model. So this behavior was first discovered by someone named Varshney. There's this whole Varshney model, but there's a modified version called the O'Donnell and Chen model. That's what the data is fitted to. And it gives you this S parameter. This S parameter is called the Wang-Rees parameter. It's a very special thing. But before I explain what it is, just note that it clearly gets bigger for the smaller particles, okay? So the Wang-Rees parameter, how do we think about that? It's a measure of how much atoms are moving in your material, how much the geometry is distorting. So if you had a large Wang-Rees parameter, as in our small nanoparticles, the geometry of your ground state is really different from the geometry of your excited state. So there's a huge distortion to your geometry. Whereas if you have a small Wang-Rees parameter, there's just a very minor shift in the position of where your atoms are. A typical Wang-Rees parameter for a molecule, so you can measure this for, if you have the optical gap for any small molecule, or even a typical semiconductor, a Wang-Rees parameter is around 1 to 10, and we're seeing values that are almost 10 times that by making the particles smaller. We see that it's really size dependent. In fact, it tracks really nicely with particle volume. So this kind of leaves this impression for us that somehow you make moth particles smaller and they get more flexible. And that was weird because, if you started in this field 10, 20 years ago and you look at a typical moth paper, the first figure that you're going to see is going to be something like this. And you're supposed to have the impression that this is a perfect representation of what happens in a moth. There's no defects. It's this like perfect crystalline lattice. Nothing is dynamic. Everything is fixed. But as coordination chemists, you can take a look at what those metal ligand bonds look like. And you know that metal carboxylate bonds are known to be really dynamic. As molecules, they constantly exist in this fluxional bonding broken equilibrium. Okay? In fact, people can measure that equilibrium. Well, this would be really important for this field because it would explain a lot of really bizarre behavior for moths. One of the things it would help explain is something that's near and dear to my heart. It's this idea of postsynthetic cation exchange. So you can take a moth, put the crystals in a solution of a different metal. The metals will swap places without destroying the moth. And we know that the moth crystals, they're not dissolving. The metals are really replacing each other. So how could that be? It's like replacing the foundation of a building without the whole thing collapsing. And so if the bonds are dynamic, that would provide somewhat of a mechanism to explain how that happens. It's also known that for some moths, the metal sites should be coordinatively saturated, and yet they're able to do the sort of catalysis that would require making metal ligand bonds with your catalyst. So there's this really nice study about the material known as MIL-47, coordinatively saturated, and it's able to perform epoxidation catalysis. And these studies showed it's probably not just defects. I mean, there's a lot of catalysis in moths that it's just missing linker defects, but this study was pretty definitive to show that it must be fluxional metal ligand bonds. There's this whole area of melting or liquid moths, porous liquids, where in the papers themselves they invoke this idea of dynamic breakable metal ligand bonds as the mechanism of how these things could melt. So this would still be strange to think about in this field, but if you're a polymer chemist, this is totally conventional. In fact, when people use metal carbene polymers or metal pyridyl polymers, they can measure those equilibrium constants. They're big, but they're measurable. And like I said, people have measured the equilibrium constant for metal carboxylate bonds, and it's tiny. a log K of 0.5 would imply that a third of the time you don't even have bonds. A third of those bonds are broken at any given time. So, so I want to be able to measure that for a moth. And we had this vague idea that, in fact, it was actually inspired by the way that they measure the equilibrium constants for this material. I figured, you know, if the bonding in a moth is dynamic, I should be able to use some kind of vibrational spectroscopy to see that. And I had this intuition that as you heat up a moth, that the vibrations, if they're really getting weaker, they should redshift. That was my intuition. And so my justification for that is these are the bonds that we want to see. These are the metal oxygen bonds we want to see. Unfortunately, the vibrations for these bonds are pretty low frequency. And you would need variable temperature Raman or variable temperature terahertz spectroscopy. I don't have access to that in my lab. So I figured, let's study this bond, the carboxylate bond. Because this is going to be much more addressable with conventional IR spectroscopy. And I figured that even though this is not the metal ligand bond, I figured a really big change to this bond should cause a small but detectable change in the carboxylate bond. The reason I thought that this would make sense, you could justify with MO theory again. So here's an MO diagram for a carboxylate bond. And you have two pairs of electrons that are sitting in orbitals that are formally anti-bonding or non-bonding with respect to the CO bond. That lone pair, these electrons here are the lone pair that sit on the oxygen that form a bond with the metal. And so my thinking was that if you have a really strong bond here, these electrons aren't spending a lot of time in those orbitals. So you have a strong CO bond. But if this bond becomes weak, those electrons are spending more time in these orbitals, and now your bond becomes weaker. And so in other words, this is a fancy way of saying when you heat up a moth, the carboxylate bonds, those vibrations should redshift, okay? That was the expectation. And so that's the experiment we did for 12 or so of the most common moths out there. Here again is our workhorse copper HKUST1. And when you measure its IR spectrum across different temperatures, this is what the data looks like. And I'm looking at this, and there are a lot of bands here to analyze, a lot of IR bands. I figured, but this is probably the asymmetric stretch, this is probably the symmetric stretch, and they redshift, but so do a lot of other bands. And so I wanted to make sure I knew what the heck was going on here. And so I worked with my excellent collaborator and colleague, Chris Hendon, who was a finalist here a couple years ago. And he helped us simulate the whole IR spectrum. And what we saw is that any band that redshifts has at least some carboxylate character. If a band has no carboxylate character, it doesn't redshift. And that's kind of special. That tells you that when you heat or cool a moth, all of the changes are all sort of absorbed and localized in those metal carboxylate bonds. Nothing else seemed to be affected. We can look at that asymmetric stretch, and when we normalize the data, it is clearly redshifting. The effect is reversible, so we aren't just introducing defects, we're not just destroying the material. But perhaps the most useful thing that we saw here was when you plot the width of the peak, the full width at half max. I thought that as you heated it up, it would just kind of get broader and broader and broader, more disorder. But instead, it was actually broadest at an intermediate temperature. It turns out that was cluing us into something important, is that we're looking at two different species here in equilibrium with each other, sort of like that bound and unbound. We figured that you had a collection of metal carboxylate bonds. They're probably, they're a little different from each other, but they're all relatively tightly bound. We call this the tight state, okay? And then if you heat up the material, we figured that you would access a whole different collection of metal ligand conformations where the bonds are a little bit weaker, okay? And when you heat up the material, those become preferred. Well, this shows up in the data. So here's the asymmetric carboxylate stretch again. We can fit it to a two species model, global fitting model. And we see that at low temperature, you prefer the high frequency species. At high temperature, you prefer the low frequency species. And at intermediate temperatures, you see both of them. And that's why the peak is broadest, because they're both there. Okay? But the other nice thing about doing this fit is that you can integrate under these peaks. And if you take the ratio of those two, there's a lot of information hiding in there. That gives us the equilibrium constant of this process, of the moth bonds being bound and unbound. Okay? And so we can plot that equilibrium constant, and we see it increases as you heat up the material. This is the inverse of, if you're familiar with stability constants, this is the inverse. So bigger K means more of the unbound. Regardless of that, you can look at the value for room temperature, and if you convert that to the stability constant, it's actually remarkably similar to reported stability constants for metal carboxylate bonds, which is weird, because this is a solid state material. And we did this with all these different common moths. So they, they all have different metal carboxylate geometries, so the IR spectra, they all look a little different, but the thing they all have in common is you heat these moths up, and the carboxylate stretches redshift reversibly. They all do the same thing. And we can perform the same analysis with all of them. And so we call this the flexibility constant. It's not the same thing as the stability constant, the flexibility constant. And so now you can say, I'm working with some moth for some catalysis purpose. Carl, how dynamic should I expect that material to be? So now I can say, well, okay, you're working with MFM 300. Now I can tell you those bonds are pretty dynamic compared to some of the others. It was nice to see that supposedly the most stable moth, UIO66, also has the largest stability constant. But it's not that big. So it implies that even in the most stable, what should be the most rigid materials, they still have this pretty strong temperature dependence. Okay, so we have that data. We wanted to dig even deeper. So with equilibrium constants versus temperature, we should be able to extract out thermodynamic information about this process. And so we tried fitting the data to a typical Van Hoff relationship. That's the fit in blue. And it was pretty lousy. We didn't really know why. And so we were looking around the literature, and it's like, what other models have people used? And there's this model where it's essentially the Van Hoff model, but they allow the specific heat of your material to change. And so we use that, and the fit, the pink line here, is a much better fit. And this model people use to study phase change materials. So when something undergoes a phase change, the specific heat changes a lot, so you have to allow the specific heat to change, which was curious. We didn't really know why we would need to use that sort of a model. The delta H and delta S values that we get out are also consistent with a phase change happening in this sort of system. And so you're wondering, okay, what do redshifting vibrations have anything to do with a phase change and this equilibrium? What's going on here? And so when we put this all together, we came across this idea that I didn't know about until we started on this project. And it's the idea of something called a soft mode. A soft mode is a vibration. So a vibration in a crystal is called a phonon. So it's a vibration that as it vibrates, it moves the position of the atoms so badly that it causes the material to fall apart. So if you've ever seen the cartoon of the opera singer singing and the wine glass vibrates, it resonates, and then it explodes, that's sort of my analogy here, except this is a reversible process and the exploding wine glass is not reversible. But this is data of two soft modes for a very common material, strontium titanate. So strontium titanate undergoes a phase change. It changes from one crystal phase to another. And there are two phonons, and you can track their frequency. And as you heat up the strontium titanate towards that phase change, you'll see that both of those phonons, they redshift until they disappear completely. The frequency goes to 0, and then above that temperature, they become a new phonon. They regain their frequency to become something else. And so the way that I like to think about this, and I saw someone write this really eloquently, is that the one way to think about it from the chemistry perspective of why that phonon is losing its frequency is because it's dissipating it to its neighbors. And so it's sort of transmitting its energy to allow that phase change to happen, okay? And so this idea of moth bonding being dynamic has inspired us to think about, can we use this to understand phase changes and design phase changes in porous materials? And so this idea of soft modes, it shows up everywhere. And so it turns out a lot of things undergo, like going back to the water analogy from yesterday, is ice will melt because there are vibrations that distort the position of the molecule so intensely that the thing rips apart and turns into liquid water. There are magnetic transitions, ferroelectric transitions. A lot of important transitions are driven by the existence of a soft mode. Okay, so we wanted to apply this principle to understand some interesting phase change materials out there. So there's a moth called iron triazolate that is a spin crossover material. And what that means is that if you can measure the magnetic moment as a function of temperature, the material would stay in a non-magnetic state, in this case, a low spin state. And then at some point, at some temperature, it flips into a high spin state. You cool it, and it'll stay in that state for a very wide temperature window until it suddenly flips back down into the low spin state. So that's peculiar behavior because other molecules or materials that undergo spin crossover, so if you have a molecular crystal and you measure its magnetic response, as you heat it up, you just get this very gradual population of the high spin state. Most spin crossover materials look something more like this. There's a hysteresis window, but it's more gradual. But the data here for iron triazolate actually looks much more like this perfect box-shaped behavior that people had predicted in the 70s. So it turns out iron triazolate has the widest hysteresis window of any spin crossover material, or one of the widest, because I know there's going to be someone out there who says, no, there's this one paper. But this is among the widest hysteresis windows and the sharpest transitions. And so in the 70s, people predicted that you would get this sort of behavior if the cooperativity in your material was 5 times the thermal energy around the material. So 5 times KT. Okay, but what is cooperativity? You know, as a chemist, when someone says something like that, it has to be intuitive to me. But apparently, based on this, cooperativity is not only a concept, it's a thermodynamic quantity that you can actually measure. So, okay, so I wanted to understand where does this behavior come from, and the other thing is I wanted to walk away from this project understanding what the heck is cooperativity. So we thought, you know, maybe dynamic metal ligand bonds had something to do with this. So we performed the same trick with iron triazolate. So we measure its IR spectrum as a function of temperature. Here's that triazolate stretch. It redshifts and blue shifts reversibly as you heat and cool the material. But something really special happens in this case. As you plot the frequency of that triazolate stretch and you heat it, it redshifts, just like we saw for the previous material. But right at the reported spin crossover temperature, you see that inversion like I showed you for strontium titanate. You can cool it, it'll blue shift, but then right at the spin crossover temperature, you get that inversion. And what this says is that the iron triazolate stretch, this dynamic stretch, is acting as a soft mode, because this is the hallmark evidence of a soft mode. Okay, so that was nice to see, and I wondered, you know, is this really unique to this material? Well, one of the nice things about iron triazolate is it belongs to a family of isostructural materials. You can make it with zinc, manganese, cobalt, copper, etc. And when you look at those, so here's the data for cobalt, here's the data for manganese. The triazolate stretches, they all redshift, so they have that dynamic character. Here's the data for zinc, it does it too, but they don't have that inversion. The only one that does is the copper version. There's a little baby kind of inversion here. Turns out the copper triazolate also undergoes a phase change. It undergoes a crystallographic phase change. It goes from cubic to tetragonal. And when it undergoes a phase change, you also get that inversion. So what this tells us is that moths because they have this intrinsic ability to have these dynamic bonds, is that if a material can undergo a phase change, that is what's going to act as the mechanism of what causes the phase change. This idea of the bonds being really weak and being able to kind of move into lots of different geometries, again, Chris provided really nice calculations to show these are all these different geometries that can exist around room temperature. I call this the haze, the LA haze. If I give a talk in Southern California, I call it, this is the LA haze. And so these are all the geometries that should be accessible around room temperature, and there's tons of different geometries. So I think at room temperature, a moth crystal is just constantly wiggling around into all these different conformations. And we can predict the energetics of the spin crossover in iron triazolate. So here's the potential energy for the low spin. Here's the potential energy surface for the high spin. We predict that they should be different by about 30 kilojoules. So delta H should be about 30 kilojoules. When we measure the spin crossover using calorimetry, we get spot on for about 30 kilojoules per mole. So this is all nice. So we think we understand this material. And so this is my proposal. Spin crossover happens here. The hysteresis arises from when you try to heat up your material, a metal site, an iron site, tries to go high spin. Everything around it is low spin. When it tries to go high spin, it really puts a lot of pressure on the crystal. And all the surrounding neighbors, they say no, and they push it back into low spin. So this is why you heat it, and it stays low spin, low spin, low spin. And then all of a sudden, it flips into high spin. And so why does that happen? Well, my argument is that because low spin to high spin necessarily means you're going from short, tight, strong bonds to long, weak bonds, the fact that moths already have this ability to kind of dynamically fluctuate between being loose and tight, that it's that ability that allows the spin crossover to happen in the material. Okay, so there's this idea of cooperativity. What the heck is this? So we're looking around more in the literature. People can measure it. They call it gamma. And you can measure it if you know, if you do the calorimetry experiment I showed you before, you can get delta H and delta S. And so at a given temperature, if you know how much of your metal sites are in the high spin state, that's this value here, you can figure out what cooperativity is. Okay. So we can do this. And as a function of temperature, we can back out what cooperativity is. And we get values of about 20 kilojoules per mole. It turns out that's exactly 5 times KT for this material. So exactly like people had predicted in the 70s, cooperativity, whatever it is, I still haven't, at this point, still hadn't figured out what it means, but it's behaving the way that it's supposed to. Well, here's my proposal. The reason that iron triazolate has such a wide hysteresis window and has such sharp transitions and has so much cooperativity is because I think moth bonding is sitting in this perfect Goldilocks regime where the bonding isn't too weak and it's not too strong. If you have a molecular crystal that undergoes spin crossover, if one of those molecules goes high spin, the neighboring molecules don't care because they're not bound to each other. In fact, the only molecules that show a hysteresis are where in the crystal structure there's hydrogen bonding or some sort of weak bonding where they influence each other. Most conventional solids don't show spin crossover. It's because the bonding it's too dense, it's too strong. If a magnetic center goes high spin, the surrounding lattice just pushes it back into the low spin. Okay, so moths sit in this perfect regime of being both weak and strong, and I think whenever you study anything in chemistry, there has to be a reason. We all focus on these really specific areas, but I think we have to learn something that should be applicable and interesting to the broader community. And so with moths, I think what's unique about them is this bonding that sits in this sort of not too weak and not too strong, and all of the interesting properties that emerge from it that you wouldn't be able to study with other molecules or materials. This behavior should be size dependent, okay? So spin crossover is thought to start at the outside of the particle, and that's because that's the most flexible place in a material, the most accommodating of becoming high spin. And so we thought if we could make this material of different sizes, that spin crossover should become size dependent. So we needed to be able to make this material of different particle sizes. So as I was showing yesterday, when you try to make iron triazolate and you follow the normal synthesis, you get this total mess. And there's no way you're going to be able to see any size-dependent behavior with this pile of bulk powder here. And so we had to figure out how to make these as nanoparticles. And so, as I showed yesterday, Checkers pioneered this idea of being able to add modulators and push those sizes from hundreds of nanometers down to just 6.5 nanometers, okay? And so now that we can make these this small, we can see what happens to their spin crossover behavior. And we see in the calorimetry data, so every time you get a dip here, it's telling you that's where the spin crossover temperature is occurring. As we move from 130 nanometers to just 6 nanometers, we see that transition drops by over 50 degrees, which is really cool. In the IR data also, so in the pink is that redshift that I showed you previously for the bulk material. And when you make it smaller, everything moves. And so it's consistent again with this idea that you make a particle smaller, the redshifting becomes, that slope becomes steeper. And one way to interpret that is the crystal's actually becoming more flexible. The spin crossover is easier to happen. All right, so the last thing I want to tell you about is the other little fun things that we can now do now that we can make these particles so small. So these particles are so small that this is what, if you want to call it a solution, looks like for 6 nanometer particles. It just looks like a totally transparent solution. You make them bigger, they get cloudier. That's what you expect. They start to scatter light. Here are the solution state UV vis spectra. Okay, so some of the only first examples of solution state spectra for a moth. This is all in comparison to the bulk spectrum in gray. These are metal ligand charge transfer bands. If you look really closely at these two bands, something unexpected happens. They're size dependent. Here's the peak position of those two bands. In fact, if you were to include the position for the bulk material, it would be way out here somewhere. So in other words, as you make the particles smaller, the position blue shifts and moves to higher energy. So of course I thought, oh my God, are we seeing quantum confinement in something that isn't just cadmium selenide? Well, the way to test that idea is you try to fit this to a 1 over radius or 1 over radius squared, and it doesn't fit. But what we think, so we don't know still what is really the root of this, but we're working with computational collaborators and experimental collaborators, and what it's looking like is that something conceptually related is happening. You have orbitals on the inside of your particle, you have orbitals on the outside, you have all your surface orbitals. And as you make your particles smaller, those two types of orbitals, they communicate with each other more and more, and they destabilize each other. And so by the time you have a 6 nanometer particle, you've really destabilized those orbitals, and you get this bigger HOMO-LUMO gap, and everything blue shifts. But that's just kind of our best guess right now. Because these are so small, we can make them as thin films, like I was showing you. And now that we can make them as thin films, we can measure their conductivity using 4-point probe contact techniques, which is much easier when you can work with thin films. And whether you're working under nitrogen or in air, we see that the conductivity really increases by simply making the particles smaller. The conductivities overall are higher in air because you need to oxidize some of those iron sites. But what we see is that when you go from the biggest particles to the smallest particles, the conductivity increases by about 2 orders of magnitude. And that was unexpected for us. But the reason lies in the fact that, as I was showing yesterday, that the particle-particle contact seems to get so much better by simply making the particles smaller. And so the transport of charges between particles becomes much more effective when they're touching each other more, essentially. The last thing that we were able to explore and have fun with is I said, if these are really like solutions, we should be able to do solution state electrochemistry on a moth. And so this is what a solution state cyclic voltammogram trace looks like for a solution, a suspension of 25 nanometer particles. And it looks surprisingly like what you would expect for a molecule, not a moth. You see multiple quasi-reversible waves. That was weird. That was unexpected because really there should be just one type of iron environment in this material. I mean, crystallographically there are two, but really they're so similar we should have just seen one. So we thought maybe this is just an impurity. Okay, so let's repeat this again. You could repeat this for all the different sizes that we can make, and we see qualitatively similar traces, multiple quasi-reversible waves. It's unexpected. And we wanted to understand what was going on here, so for more sort of a quantitative insight, we took advantage of the fact that we can make them as thin films. And so we cast them as thin films on an electrode. We repeated the measurement, this time in acetonitrile so that the particles don't dissolve. We see a CV trace that's qualitatively similar, multiple quasi-reversible waves separated by half a volt or so. And then we started to think, you know, the pore sizes in iron triazolate are really small. How is PF6, our anion in the electrolyte, how is it charge compensating the iron 3+ when we try to oxidize the material? Maybe PF6 simply isn't able to get inside. So we thought, what happens if we move to simply a smaller anion? And so when we move to a smaller anion, BF4, everything changes. The peaks become sharper, there's more of them, and depending on how you assign them, everything shifts to less positive potentials, meaning it becomes easier to oxidize this thing. And so it started to suggest to us that really the pores are sort of controlling the redox chemistry in this material. And if that's true, you should be able to see the ions intercalate. You could do this using a special electrode called quartz crystal microbalance electrode. You can use it like a normal electrode. These are the CV traces that you get when you use it like a normal electrode. So it looks similar to before, except what's special about a QCM electrode is you can actually detect the mass of your material during this. And so when we measure the mass at the same time as doing this experiment, we see that in both cases the mass increases as you oxidize your material, which is good because as you're making iron 3+, the anion should be moving on the inside, but there's a much greater mass increase in the case of BF4, in particular at this really positive feature here. And so this has painted this picture to us that I was telling you about yesterday, that even though we're really talking about what should be the same material everywhere in the film, by being able to control this more of a macroscopic picture of what's happening here, we can engineer in this additional 1 volt potential to say, to drive the BF4, not just from the surface of the film, but onto the inside, without changing anything else about the material, is where that 1.2 volt came, over potential came from, and the origin of that massive redox potential that I was telling you about before. And so hopefully I've shown you that by developing a new model of understanding how these particles grow, we're able to control their sizes. We're able to do things like solution state spectroscopy that people hadn't really been able to do up to this point. And we're just beginning to understand some of their size-dependent behavior that is opening a lot of really cool directions in our lab, and I hope to inspire for you guys as well. With that, thank you for your time. Thank you so much for the award. I don't know if there's time for questions, but I'd be happy to answer questions also. Thank you.
Thank you, Carl. I learned a lot. Well, it seems that you really have a good touch for chemistry. You feel it,
yeah,
right? That also helps in science to, if you can visualize what you actually calculate or measure, and it was quite clear. So, guys, we open the discussion. Well, I can actually start.
Okay.
You know, all the time I was giving the microphone to others, and I decided that I would start the first one. You started with this membrane technology, okay? And that it is really needed to make a separation process, but that they are brittle and delicate. And then all your talk was actually about how brittle these materials are, how, you know, how easy it is to destroy them.
Yeah.
So, you know, I sort of expected that at the end it will be like, and look, and I changed this, and now this is a perfect membrane. So Where's the perfect membrane of
Yeah,
moths?
yeah. So, I think this idea that the bonding is dynamic might actually become an advantage when making the membranes. I think it's going to allow us to form covalent linkages with the polymer, or maybe heal in response to a break. Just the fact that you have this sort of reversible on-off, I think is actually gonna help in that regard. I mean, I hesitate to call that bound and unbound. It really is just sort of this is why we call it the flexibility constant. They're sort of able to rearrange in response to temperature without falling apart. Yeah.
Yeah, so it would be healing, right?
Healing,
so
right?
Even if the membrane sort of locally breaks at the nanometer scale, it would. So will you make a material like that?
That's the goal. In response to light, in response to temperature. In fact, one of the very first things that we started doing in this lab our dream is that we can make a material like this and sort of scratch it and apply some stimulus, heat or light, or maybe just solvent if solvent has a big role here, and to see that material heal. So that is one of our dreams in the lab. Yeah.
Questions, comments?
Hi, thank you very much for the very interesting lecture. Whoa. Okay, I have a question. You put down the size of moth crystals, yeah? So the smallest, maybe, just the smallest moth crystal is just simply one pore, and this is just metal organic cages. So could you try to compare could you try to see these metal organic cages as the smallest possible moth nanoparticle and compare some your size dependence properties?
Yeah. That's a really interesting question. We haven't worked with those cages, but it relates to this idea of what is the smallest possible size. And I think it's no coincidence that iron triazolate is a really dense material. In 5.5 nanometers, you wouldn't be able to fit a lot of moth if it was a normal moth, like if the pore was a nanometer wide or 2 nanometers wide. But here we're talking about pores that give rise to this kind of gating effect in the electrochemistry that are only about 4.5 angstroms. And so I think there's a relationship there. With a normal moth, the smallest sizes that we can get are about 20 nanometers. And so is that because there's some limitation to, if you're going to make a moth particle, you need to have some baseline number of pores for it to actually be a crystal. But it'd be really interesting to see how all of this compares to the extreme limit of a single cage. Yeah.
Okay, thank you.
Yeah, cool talk. Thanks, Carl. So, if you're dreaming at night and you showed us yesterday, I think your days are okay too.
Okay.
You showed this hysteresis, and you brought the analogy with ice melting to water. So, in this classic transition, right, there's asymmetry. You can supercool water, but you cannot overheat ice. So, do you see the same asymmetry here, or you can, overheat your system? Which way is the hysteresis, right?
Yeah,
I mean, is it symmetric or asymmetric?
Huh. I haven't seen that in magnetic data. That's an interesting question, though.
Because it would seem to me that it should be similar here, right?
Yeah,
I mean,
yeah.
it's different to expanding the system and,
right.
and compacting it, because the potential is asymmetric, right?
Yeah.
It's always hard wall for compaction, while it's kind of softer to expand. So
Yeah, right,
it
right,
should be
right.
symmetric.
Yeah,
right?
that's a really interesting point. I haven't seen that borne out in the data, but it seems like you should be able to. Yeah, that's a really cool point.
Well, you should know where the temperature of the phase transition is, right?
Yeah,
and you
yeah.
can see which way the hysteresis goes on which side you are, like in ice melting, right?
Yeah,
That you can supercool water to -40, but you can never overheat ice above 0, right? So, so I don't know.
Yeah.
Okay,
Yeah.
just an idea.
Yeah.
Yeah, thanks for a very cool talk. Returning to your electrochemical data there, I was wondering if you would have, I've never worked with MOFs, so maybe this is not possible, but if you would create MOFs with different size of, where you have several sizes of of cavities, would you be able to see several steps of inclusion peaks then? And also, if you have larger if you have these, would you see sort of shell things that you would see? Now you can push the liquid into the first sort of shell of the particles and then go further in.
Yeah, that's a great suggestion. We're working on growing core shell structures. For one reason being to turn off any redox chemistry. So one of the things we're trying to do is to coat the particles with like the zinc version or the cadmium version. But by simply altering what the metal identity is, the pore actually can open up quite a bit. So iron happens to be the smallest or one of the smallest of these. But there are other redox active versions. So cobalt is redox active, manganese is redox active. But those pores seem to be just big enough that PF6 can easily come in and out. And so when we measure the electrochemical response, I didn't show the data, it's just one feature. And so I think is further to the point that by having the pore of just the right size, you open up this huge overpotential for that process to happen. But it'd be cool, if there were multiple pores and maybe ions of different sizes, and yeah, that'd be cool.
You were talking about dynamics without explicitly mentioning the time scale. Could you be less mysterious about it?
Yeah. So I've gotten this question before. We are not referring to the kinetics of the process. By dynamics, I mean hemilability. Yeah, just the reversibility of the process. But in terms of time scale, the closest I've seen to someone trying to approximate this is molecular dynamic simulations.
How about time results IR spectroscopy?
Yeah. Yeah. No, we would love to do that. I don't have a good guess for what the time scale would be, but that would be a great way to do it. Yeah.
Okay, thanks.
Other questions, comments? Yes.
Thank you for the inspiration. I have two practical for me and short questions. I didn't get it all. And which compounds can act as modulators?
Yeah, so in that case, we were using something. So a best guess, like a first order approximation, is something that looks like your linker. But that's kind of actually still an open question. Because as I was saying, a modulator acts as an acid or a base, or it acts as a ligand. And we've tried to decouple this. In fact, iron triazolate can be made with modulators that don't look anything like triazolate. It can be made with N-butylamine. It can be made with, it turns out what really seems to matter is this idea of depleting the local concentration of metal ions. So one of the ways that we've made some of the isostructural versions of this material is by starting with a metal precursor that is so hard to dissolve that just by metal just very slowly kind of leaching into solution allows us to make the nanocrystals. But in terms of modulators, it is still this question of like how much does it have to look like your linker? And then in terms of pKa, how much does it have to look like your linker? Yeah.
Okay, thanks. And another one, how exactly do you measure the size of the moth crystals? By the microscopic?
Yeah, so we'll get what's called the Schur size from analyzing the peak width of the diffraction, but that just tells you the crystallite domain size, the average size of the coherently scattering crystallite domain, and then we'll pair that with SEM to get a sense of what the particle size is. But we care a lot about what happens in the solvation shell around if you want to call it that, around the particle. So then we'll use dynamic light scattering. Yeah, it's like sort of a complementary set of perspectives.
Okay, thank you very much.
Mm-hmm.
Yes, okay.
Is the effective J coupling between the iron centers also size dependent on the moth molecules? It should be more or less constant, but I'm really curious about this.
I would expect it to be constant. In fact, I think a lot of the size dependence we see is arising from the surface, but that doesn't mean that we're only seeing the effect of the surface. I think it depends on what I'm talking, whether it's magnetism, whatever, but you have some sort of defective geometry or what, maybe interfacial dipoles or whatever, and I think when you have more and more of that surface, then you impact everything on the inside. But I think everything on the inside probably isn't changing very much.
Okay, and
Yeah.
what is the order of these J couplings? Have you
Oh.
done any susceptibility measurements on this?
I haven't, but people definitely
Okay.
have. Yeah, it's a hot area in the moth. Yeah.
Okay, thanks.